Welcome to this first video about the best methods for converting aldehydes into secondary alcohols. The reaction of aldehydes with carbon nucleophiles is one of the easiest and most versatile ways to form carbon-carbon bonds, and a large number of variations have been reported. And because most secondary alcohols are chiral, most of these reactions can also be conducted enantioselectively. I've organized this vast subject into 10 chapters, starting with the addition to aldehydes of various organometallic reagents, followed by different types of enolates, and finally of arenes. In other words, I begin with the most reactive nucleophiles, which tend to yield stable alcohols, and proceed to weaker nucleophiles, which often yield less stable alcohols with a high tendency to undergo elimination or acid-mediated SN2 displacements. This present video is about the addition to aldehydes of polar non-stabilized organometallics, such as organoalkali or Grignard reagents. Because polar organometallics are readily accessible, for instance from halides and metals or by transmetallation, this is a valuable reaction for the construction of more elaborate carbon frameworks. The resulting secondary alcohols are also versatile synthetic intermediates and can, for example, be oxidized to ketones or converted into alkenes, halides, amines, nitriles, and many other functional groups. With polar organometallics, I refer to organometallic compounds with a strongly polarized carbon-metal bond and the partial negative charge mainly localized at carbon. Such compounds are usually prepared by deprotonation or from an organic halide. Stereochemically, deprotonations proceed mostly with retention of configuration. This will of course only be observable if the resulting organometallic reagent is kept sufficiently cold to remain configurationally stable. Because of the weak carbon-metal bond, most polar organometallics will epimerize quickly at room or slightly elevated temperature. Chelate formation can, however, increase their configurational stability. When polar organometallics are prepared from secondary or tertiary alkyl halides, stereochemical retention or racemization is usually observed. Most polar organometallics form aggregates of 2 or more molecules, and these aggregates are less reactive than the monomeric form. Solvents have therefore a strong impact on the reactivity of polar organometallics, and best results are often obtained in diethyl ether or in THF, which can dissolve these reagents and assist their disaggregation. When polar organometallics add to aldehydes or ketones, first a metal-oxygen bond is formed, what increases the electrophilicity of the carbonyl group. The carbon nucleophile is then transferred to the electrophilic carbon, and a metal alcoholate results. The stereochemical fate of the nucleophilic carbon atom is either retention or inversion of configuration. Polar organometallics are also strong bases, and when an aldehyde is particularly acidic or highly enolized, deprotonation instead of addition can occur. In such instances, a less basic organometallic reagent may be helpful, for instance an organotitanium or organoaluminum reagent. The main advantages of the preparation of secondary alcohols from polar organometallics is the ready availability of these reagents and that the reactions proceed quickly, even at low temperature. Problematic are the occasional low yields and that anhydrous solvents and an inert atmosphere are usually required. Then, because of the high reactivity, most polar organometallics show low chemoselectivity. In Organic Synthesis, a freely available online collection of tested procedures, there are numerous examples of the addition of polar organometallics to aldehydes. I've chosen a few with particularly demanding aldehydes, such as this one with acetaldehyde, which is tricky to handle because of its low boiling point, high acidity, and high tendency to oligomerize. Nevertheless, as shown here, aryl Grignard reagents add cleanly to acetaldehyde in diethyl ether to yield the expected benzylic alcohols. In this example, an alkyl Grignard reagent was added to metacrolene. No addition to the electron-deficient olefin occurred, and only the product of 1,2 addition to the carbonyl group was obtained. Traces of soft transition metals can, however, readily cause problems by increasing the extent of conjugate addition to the double bond. This is a more recent example of the catalyzed enantioselective addition of an organotitanium reagent to cinnamaldehyde. Unfortunately, a large amount of chiral ligand was required, the enantiomeric excess was low, and with enolizable aldehydes such as heptanal, only a yield of 15% was attained. For such reactions to succeed, the complex formed from the chiral catalyst and the nucleophile, in this instance a butyl-titanium derivative, must react faster with the electrophile than any carbon nucleophile that is not complexed with the chiral catalyst. This example suggests that butyl-titanium complexes with binaphthol react faster than butyl-titanium isopropoxide complexes. Better results than on the previous slide were achieved with the chiral amino alcohol as catalyst and diethyl zinc as nucleophile. Here, even enolizable aldehydes gave acceptable yields, and in some instances high enantiomeric excess. In this remarkable example, phenylacetaldehyde could be converted into an enantiomerically enriched secondary alcohol in high yield by using methyl aluminum and titanium reagents and a chiral diol as catalyst. Phenylacetaldehyde is a particularly tricky acidic aldehyde with a high tendency to dimerize by aldol addition. Here, only 2% of chiral diol was sufficient to add a butyl group to metacrolein with high enantioselectivity. Again, no product from conjugate addition was isolated. Because of the high basicity and reactivity of polar organometallics, numerous side reactions can occur and lower the yields. When preparing secondary alcohols from Grignard reagents, the intermediate magnesium alcoholates are powerful hydride donors and may be oxidized by the starting aldehyde, what would be a variation of the Oppenauer oxidation. The resulting ketone can react with a further equivalent of Grignard reagent and yield a tertiary alcohol, or add to the starting aldehyde and yield further byproducts. Polar organometallics are powerful reducing agents that can be oxidized either by hydride or single electron abstraction. Oxidation may occur, for instance, if the electrophile is sterically demanding and CC bond formation therefore slow. In such instances, a single electron or hydride transfer can compete with the expected CC bond formation. Radicals formed by single electron transfer may add to alkenes present in the reaction mixture, react with oxygen to yield hydroperoxides, or dimerize. Alpha amino acids are readily available and can be converted into alpha aminoaldehydes by reduction and Swern oxidation. These aldehydes are valuable synthetic intermediates that can be easily converted into a large number of different products. Upon reaction with carbon nucleophiles, however, alpha aminoaldehydes can yield unexpected products because of their ability to rearrange under various conditions. As already mentioned, deprotonation of the aldehyde and conjugate addition to electron-deficient doubled or triple bonds are further potential side reactions of polar organometallics. These can also add to electron-deficient arenes and yield dihydroarenes or products of aromatic nucleophilic substitution if the arene has suitable leaving groups. Because of their high reactivity, polar organometallics can react with many functional groups, for instance with nitro groups, carboxylic esters, carboxylate salts, nitriles, ketones, epoxides, and alkyl halides. Although acetals are usually used to protect ketones or aldehydes from nucleophilic attack, some acetals, aminals, and orthoesters do react with sufficiently nucleophilic organometallics. The reaction of Grignard reagents with orthoesters is, for instance, a useful procedure for the preparation of acetals. Some polar organometallics have a high tendency to eliminate hydride and may act as hydride donors instead of carbon nucleophiles. Occasionally, even deprotonated amines, such as LDA, can act as hydride donors and reduce aldehydes to primary alcohols. Here are some more examples, in particular of asymmetric additions to aldehydes, but many more have been reported. In order to lower their reactivity and enhance their selectivity, in many of the newer examples, organolithium or magnesium reagents are transmetallated into organotitanium or zinc reagents. Organoaluminum reagents can also be prepared this way, but these are rather unreactive and have only rarely been used as carbon nucleophiles. In the next video, I'll present the use of boranes as carbon nucleophiles. As you'll see, these are much less basic and display a completely different reactivity than polar organometallics and can be a valuable alternative when dealing with particularly base-sensitive aldehydes.